Okay, so this first question says that common tests such as the SAT, ACT, LSAT, and MCAT, there are multiple choice questions with the possible answers of being A, B, C, D, or E. Each question only has one correct answer. So we assume that somebody is taking one of these exams and is randomly guessing on each question, independent of any other question responses. They just randomly guess on each one. So if X represents the number of correctly guessed questions in a block of 100 questions, what is the distribution of X? Check any relevant criteria. What is the mean and standard deviation of X? So we get that either the question is right or wrong. So we're going to count the number of correctly guessed questions. There's 100 questions total. If we have a 1 in 5 chance of guessing it right, there's a fixed probability of success. This is all things pointing towards binomial. So let's just check the criteria first. So the first criteria for checking if something is a binomial distribution is that it has a fixed number of trials. And in that case, we do. We have that n is equal to 100. We have that the trials are independent. And that's true because we're randomly guessing. As in the guess on the third problem does not affect what I guess on the fourth problem. So each trial is independent. The third is that the outcome of the trials is binary. So we have that we either get the answers correct, or we get them wrong. And lastly, we have a fixed probability of success. Which there's 5 possible answers. So there's a 1 in 5 chance, which means that P is fixed at 0.2 for each trial. So these are the 4 criteria that we need to check to say it's a binomial distribution. So X is distributed as binomial with n equals 100 and standard deviation, probability of success 0.2. Now we need to find the mean and the standard deviation. So the mean is equal to NP, which is equal to 100 times 0.2, which is just 20. And if you don't remember this is on the formula sheet. Standard deviation is the square root of NPQ, which is equal to the square root of 100 times 0.2 times 0.8 is actually 16. So the square root of 16 is 4. Okay, so X is a binomial distribution. Part B says to write down a summation of terms that would represent the exact probability of getting at least 25 correctly guessed answers. And let's see. So somebody asked, what is Q? And that's a good question. So Q, I'll write that better. Q is just shorthand notation for 1 minus P. So the opposite of the probability of success, the probability of failure. Okay, so so N was 100, P was 0.2, which means Q was 0.8. So now part B, write down the summation of terms that would represent the exact probability of getting at least 25 correctly guessed answers. I do not need to evaluate the sum. So the probability of getting at least 25 correctly guessed answers in math notation, we would say that's the probability of X being greater than or equal to 25, which this would be the sum of the probability that X equals 25 plus the probability that X equals 26 plus yeah, so on and so forth up until the probability of x equaling 100. But just to have like a little bit less terms, we could write this as 1 minus the probability that x is less than 25. So 1 minus the complement, which this is a discrete random variable. X is binomial, it's discrete. So this is equal to the probability that, or is 1 minus the probability that x is less than or equal to 24. And that's because x can only take on integer values. It can only be 1, 2, 3, 4. It can also be 0, 1, 2, 3, 4. So being less than 25 means it's less than or equal to 24. So writing this out, this is equal to 1 minus, and then we could expand this guy as the probability that x equals 0 plus the probability that x equals 1 plus, and then I'm not going to write out all these terms, actually, just put a dot, 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 plus probability that x equals 24. And then close the bracket there. And, this is just a question that I made up, so maybe it would be confusing to go further from here. But to go further, I'm going to actually evaluate these probability of x equals 0, probability of x equals 1. Not entirely, but this would be a formula for each of these where we have that it's 100 choose 0 for this first one times the probability of success, p, 0.2 to the 0, because we have 0 here, probability of failure, so 0.8 to the 100. Now this is plus, moving on to this term, we'd have 100 choose 1 times 0.2 to the 1 times 0.8 to the 100 minus 1, which is 99. And then plus dot, dot, dot. So dot, dot, dots for all those. Then this term, we would have plus 100 choose 24. 24 times the probability of success, 0.2 to the power of 24 times 0.8 to the power of 100 minus 24, which is 76. So this would be, in theory, if we computed all of these values and then 100 choose 0, 100 choose 1, 100 choose 24, those could be computed as factorials, right? This would be a nightmare to compute by hand. So moving on to part C then, instead of doing something like this, got a question. So the first question I got was, would we have to write it out that far? I don't think so. I don't think that this part B will be something that you get asked. I don't know, because I have never seen the exam, but I doubt it. This is just me kind of, showing why we even do this approximation with, that's what this is supposed to illustrate, because this would be a huge pain. So the next question I got was, would the answer in the part in the middle or the last, I'm not actually sure, be the part in the middle or the last part. Oh, okay. Yeah, I think that's just tying into the same question. I don't think that something like this will get asked. Or if it would get asked, it would be more clear on what your final answer should be between the second and the third line. So again, yeah, this is just a question that I made up. So yeah. So part C. Now, what would an appropriate distribution be to approximate the distribution of X? Include any parameter values. Check any relevant criteria. So the whole idea of binomial approximations, we have a binomial distribution here, is if the number of trials is large enough, we can approximate it with a normal distribution. So the criteria that we need to check. So criteria is that n times p is greater than or equal to 5, and n times q, which is equal to n times 1 minus p, that is greater than or equal to 5. So both of these need to be satisfied at the same time. So we have 100 times 0.2 is equal to 20, which is greater than or equal to 5. So that's good. And then 100 times 0.8, which is equal to 80, is greater than or equal to 5. So our n is large enough so that we can approximate x with a random variable y that is distributed normally with the mean of x and the standard deviation of x. So n times p times q, which in part A, we found what np and n square root of npq are. So this is equal to a normal distribution with mean 20 and standard deviation 4. So somebody in the chat asked, what's the rule for it to be large enough where it has to be greater than 30? And is it related to this? So that's a great question. The greater than 30, that's for when you take a mean. So when you have like some number of respondents and you take their, or not respondents, but you take some sample from some distribution and you took the mean of that sample, then if that's greater than 30, the sample size there, then you would say that your sample mean is distributed normally. So this is related to that because this is also a criteria where we're essentially saying, is n big enough? Because p is, probability of success, that's something we can't really control. Like in this problem, p is always going to be 0.2, but we could just randomly guess on more questions. So if we randomly guess on enough questions, then this problem turns into something we could approximate with a binomial distribution. Yeah, so this is specifically, this criteria here is for binomial approximation. And the n greater than 30 is if you're taking the mean of something and you want to say that the sample mean is normally distributed. Okay, so now we're going to find the approximate probability of getting at least 25 correctly guessed answers. So we want to approximate the probability that x is greater than or equal to 25. So like before, I'm going to do 1 minus the probability that x is less than or equal to 24. And from above, we get to approximate x with this distribution here. But we also need to account for this idea of continuity correction, which is also something I talk about in that previous video that I sent to you all. So actually not a hard equal sign. This is an approximately equal to 1 minus the probability of our new random variable that's normally distributed, y, being less than or equal to, and it's going to be 24.5. So this 24.5, this comes from continuity correction. And again, you can check out that video I sent that explains where this like 24.5 would come from, and try to think about it. If we wanted to figure out the probability of x being less than 24 and x is binomial, then when we shift to the perspective of this normal distribution, we need to do from 24.5 to get a better approximation, essentially. And yeah. So now, right, this is just turned into a z-score problem. So we do z is equal to 24.5 minus our mean was 20. So 20 divided by, and the standard deviation was 4. So this is equal to 4.5 divided by 4, which I need to pull out my calculator. 4.5 divided by 4. This is equal to 1.125. And remember, for z-scores, we round up to 2 decimal places, or round up or round down, round in the appropriate manner. So we got a 5 here. So this is 1.13. So now we have that this probability here is equal to 1 minus the probability of z being less than 1.13. And now we go to the standard normal table. So 1.1 and then 3. So we have 0.8708. So this is equal to 1 minus 0.8708, which is equal to 0.1292. So this is our approximate probability. And yeah, to illustrate that this is a decent a decent approximation, I'm gonna just show you in Excel real quick. So in Excel, the probability that we wanted to compute from before, so the exact probability, if you remember, so 1 minus the probability that x is less than or equal to 24, we can use this binom.dist function, and binom.dist, and then the, oh, I forgot the equal sign. So the arguments, the number of successes was 24, the number of trials was 100, probability of success is 0.2, and the cumulative argument set that to true. So it does the probability of x being less than or equal to 24. And we get 0.13. Now, I also want to show you what the exact answer you get using the normal distribution, because our answer is still even a little bit further off from that. Norm.dist. So now replacing essentially the replacing this binomial part with a normal part. Escape equals 1 minus, so norm.dist of now the continuity corrected part, so 24.5, and then the mean was 100, or it's 20. The standard deviation was 4, and again cumulative argument to true. And you can see these are really close, 0.131 and 130. And why this answer here is not the exact answer that we got for this problem. We get 1.130 here, but if I switch back now, my share to the screen, it's because of this rounding here. We went from 1.125 to 1.13, so that rounding actually made our answer a little bit different, but still pretty close to 0.13. Okay, so that is the binomial approximation problem. Now move on. This is just a normal distribution type problem. So we have that the Santa Barbara half marathon takes place every year in November. It is known that the finishing times for runners follows a normal distribution with a mean value of 127.9 minutes and standard deviation of 6 minutes. So what is the probability that a randomly selected runner will run at least 141 minutes, 141.4 minutes? So at least means that, well, actually the context of this problem, since it's running, is a little bit ambiguous, right? say at least 141.4, normally that would mean that, we're looking for the probability that X is greater than or equal to 141.4. But in terms of running, you'd want a shorter time when you say at least, I feel like. But disregarding that ambiguity, that's something you could ask during the exam if you were confused, if there was a context like this. We'll just roll with the fact that, it would look like this, keeping it consistent of X being greater than or equal to 141.4. So this is going to be where we find the z-score. So z is equal to 141.4 minus the mean 127.9 divided by 6. So I'm going to do that in my calculator. 141.4 minus 127.9 divided by 6. You get 2.25. And so this is equal to 1 minus the probability that X is less than 141.4, which would be equal to 1 minus the probability that Z is less than 2.25. So go to the table, 2.2, and then 0, 1, 2, 3, 4, 5, 0.9878. So it's equal to 1 minus 0.9878, which is equal to, let's do 1 minus 0.9878. 0.0122. Okay, now we want to find what is the probability that a randomly selected finisher finishes with a time between 134.2 and 141.4. So this is going to be the probability that X is less than 141.4 minus the lower probability, so probability that X is less than 134.2. This part we just found an A, so that's 0.9878. So we just need to find a z-score for 134.2. So 134.2 minus 127.9 divided by 6. So 134.2 minus 127.9 divided by 6 is 1.05. So we have that probability of Z being less than 1.05 is equal to, go to the table, 1.05, so 0.8531. So 0.8531. So our answer is 0.9878 minus 0.8531. And let's do that real quick. 8531. 0.1347. And what is the slowest finishing time a runner could have and still be faster than 95% of other runners? So we want to find some value, little x, such that this probability is equal to 0.95. Essentially, we're finding the 95th percentile, so P95. So what do? We do that for a z-score instead, and then we transfer the z-score back to x. So probability that z less than z is equal to 0.95. And we go to the table, and maybe you've actually memorized this number at this point, but it's 1.645. So you see that's halfway, 1.64 and 1.65. splits that perfectly. So let's go with Z is equal to 1.645. Now Z is equal to X minus mu over sigma. So this is equal to X minus 127.9 over 6. And that's equal to the Z-score. The Z-score is 1.645. So X is equal to 1.645 times 6 plus 127.9. And do this on my calculator real quick. 1.645 times 6 plus 127.9. And this is equal to 137.77 minutes. So somebody just asked a question. When do you know when to subtract the percent from the 1 or leave it as 95? Like, when would it be 0.5? So basically, you have to just think of the context of the problem. So if we line up if we were to draw essentially a picture to help ourselves. So we had some normal distribution, and the x-axis here is representing running times. And being faster than 95%, oh, actually, you're totally right. I just did this problem wrong. And that's what I get for, I actually didn't do these problems beforehand. So it's good that somebody just pointed that out. Yeah, if you're faster, then you're actually going to be in the lower times. So if you're faster than 95%, that means that the 95% would be this way. You're faster than 95%, which means you would be looking for the 5th percentile. So we get that. And so I'm glad that somebody just pointed that out. Let's redo this problem then. So erase all this stuff. This was all wrong. And but I hope that made sense, and thank you for pointing that out. So again, this needs to, I guess I should have done that from the beginning. So 0.05. And now we do the opposite. So actually, this is going to be pretty similar to do. So probability that z less than z is going to be 0.05. Because of the symmetry of this bell curve, before we got that z was 1.645. But because of the symmetry, we have that z is going to be negative 1.645. So that's going to be the difference. And just to verify that, let's go to negative 1.64. And you can see 0.05 and 0.0505 and 0.0495. So between negative 1.645 is what the number we're looking for. So essentially everything is the same. Z is equal to x minus mu over sigma, which is equal to x minus 127.9 divided by 6 is equal to the z-score is now negative 1.645. So x is equal to 1.645 negative times 6 plus 127.9 and 0.6 or 6 times 1.645 and then plus 127.9 is equal to 118.03 minutes. So again, thank you for pointing that out. But yeah, to answer the question, when you are addressed with a word problem like this, don't be like me and just assume that 95% means 95th percentile. Actually think of the context of the problem. You're running faster than 95% of the other runners. So that means that you would be looking for the 5th percentile. Great. Okay, so now part D, if we take a random sample of 9 runners, what is the probability that their mean finishing time is between 123 and 127? So now, before we had that X was distributed normally with mean 127.9 and standard deviation 6. If we take a mean of 9 runners, then we have that X bar is our new random variable that we're working with. And that's going to be distributed normally with the same mean and standard deviation of 6 divided by the square root of 9. And so I got a question in the chat asking what worksheet is currently being worked on and where is it found. It's one that I just created within the last hour, and it's further up in the chat. You can find the Google Drive link. And I will also share that link to the blank PDF, and I'll share my solutions that I work out afterwards. So yeah, this is what we have going on. So square root of 9 is 3, and 6 divided by 3 is 2. Somebody asked, where did I get the 127.9 again? And that was from the problem. I hope I remembered it right. Yeah, got a mean value of 127.9. It tells us that from the get-go. And the standard deviation is 6. So this was our original distribution. When we take 9 measurements from this distribution and we mean them, then that random variable would have this distribution. And this relates to what somebody else said earlier about the 30, the sample size being 30. And notice that our sample size is not 30 here. But why we can say that this is normally distributed is because the original distribution is normal. We're told that it's a normal distribution. So when your original distribution is normal, any sample size with a mean will give a normal distribution. If X was not normal, then you need your sample size to be greater than 30 to say that X bar is normally distributed. Okay, so now, yeah, let's continue. Probability that X bar is between 123 and 127 equal to probability that X bar is less than 127 minus probability that X bar is less than 123. And now we need to make 2 different z-scores. So z1 is equal to 127 minus 127.9 divided by, remember this standard deviation here, it evaluates to 2. So our new standard deviation that we're working with is 2. So negative 0.9 divided by 2 is negative 0.45. And Z2 is 123 minus 127.9 divided by 2. And let's do that. 123 minus 127.9 divided by 2 is negative 2.45. So we have that this is the probability that Z is less than negative 0.45 minus the probability that Z is less than negative 2.45. Let's find out what those are. Okay, false alarm in the chat, I think, or maybe it was a typing error. So negative 0.45. So 0.401234, 0.3264. So 0.3264. And the next one, negative 2.45. So negative 2.4 and 5.0071. Minus 0.0071. So now 3264 minus 0.0071, we get this is equal to 0.3193. Okay, cool. And I'm also gonna emphasize that that's a point there. All right, now let's do the last problem. So this is the one where it's going to look different for you guys in the file, where there's different sample sizes. You have some sample sizes that are in the 300s, and I just changed that last second so that they actually show up on the table. Again, I'll share the updated file after this. So let's read this. In a study designed to test the effectiveness of echinacea for treating upper respiratory tract infections in children, 101 children were treated with echinacea, while 81 other children were given a placebo. The number of days of peak severity of symptoms for the echinacea treatment group had a mean of 6 and a standard deviation of 2.3. The number of days of peak severity of symptoms for the placebo group had a mean of 6.1, a standard deviation of 2.4. And these are all with respect, it says mean and standard deviation and mean and standard deviation, but be thinking these are sample means and sample standard deviations because it's with respect to this treatment groups that we're talking about. So we need to construct a 95% confidence interval for the mean number of days of peak severity symptoms for those who were given a placebo. So this is a sample that we're dealing with, and we're trying to find a confidence interval of the mean. So X bar is the start of our confidence interval, as opposed to P hat, which would be a proportion. So if we're looking for a mean, it's X bar. So X bar plus or minus. And then now we need to know, is this going to be T or is this going to be Z? And because we're working with a sample, this is going to be T. So T sub alpha over 2, comma n minus 1. And then sample means we're working with the sample standard deviation. So S divided by square root n. This is the general form of our confidence interval. So alpha is equal to 0.05, which means that T sub 0.025, T sub alpha over 2, and the placebo group, had 81 children. So 81 minus 1, we have 80 degrees of freedom. So we're going to use a table, and this is a different table than what you'll be given, but it's essentially the same thing. This is just the one I found online to then have in the PDF format. So we're looking for the one tail area. So that's something to note. Notice how there's like the one tail and the two tails area. And that is important to know. If you're doing alpha over 2 is one tail area. So when you look it up in the table, alpha over 2 is one tail area. If you were using just alpha, if you were looking for 0.05, it would be two tail area. So we're looking for the one tail area of 0.025, which corresponds to the two tail area of 0.05, our alpha. So this is our column we're looking at. And then we're going to go all the way down to 80 is our degrees of freedom. So making sure I'm in the right column. There we go. 80, so 1.990. Make sure again that that's the right column. Yes. So our T value is 1.990. And that's all we need. So we have that X bar in the placebo group. Let's make sure again, placebo group had a mean of 6.1 and standard deviation 2.4. So this is going to be 6.1 plus or minus 1.99, our t value, times 2.4 sample standard deviation divided by square root of 81. And computing this out, this is 6.1 plus or minus, let's do the calculation, 2.4 divided by 9, at least 81 is a perfect square, so that's kind of nice, times 1.99, so 0.53. And this is then equal to, so we can write it as an interval, write it in brackets, or I'll write it in another form that you may see too, in case you're more familiar with it. So 0.53, so 6.1 minus 0.53 is 5.57. And then 6.1 plus 0.53 would be 6.63. And got something in the chat. So we got a question asking, what does S stand for in the general equation? So S is sample standard deviation. And somebody also asked, okay, getting a few questions here in the chat. So first one says, could you go over what it says in the formula after T? As in go over the numbers here, or after T, the subscript, or this part, or which part after T? Okay, yeah. So, okay, yeah. I'll write this down below. Somebody wants to essentially go over like the subscript part, and then I'll get to the next question after that. So the subscript in the T, right, I'll write it down here. So T sub alpha over 2 and sub n minus 1. So this is all just like one big subscript, and alpha over 2 is, half the significance level. And n minus 1 is degrees of freedom. And so those are like what these are. Essentially, what you want to know about them is alpha over 2 in the table tells you the column to look in. So the significance level, and then n minus 1 tells you the row in the table. So let's go back to the table. So the significance level up here, this one tail area, this is like our alpha stuff. The one tail is alpha over 2. If we wanted to think in terms of just alpha, it would be, we look at the two tail area part. So these bolded numbers are the alpha, or alpha over 2, and then df here, the rows, df stands for degrees of freedom. So this is an n minus 1, these numbers here. Okay, and now let me pull up what the other question was. So yeah, somebody asked, how do I know if I divide by alpha over 2 or not? And essentially it's just up to you. It depends on your table, essentially. For the standard normal table, you guys have different ones, different tables than me, but you can see this table has alpha over 2 here and alpha here. So you use whatever one you want. You just need to know which, column you're going to be looking in. For the standard normal table, when you have like the confidence value for like the z score, like a z sub alpha over 2, those usually are given in terms of alpha over 2. So that's when you would use alpha over 2. But yeah, just read the table and make sure you know like what it's asking or what it tells you. Okay. And somebody asked, how do we decide whether a problem is one-tailed or two-tailed? So in general, with confidence intervals, the critical value you're looking for, this z sub alpha over 2 or the t sub alpha over 2, is two-tailed. But is a two-tailed problem. I wouldn't worry so much about one-tail versus two-tail yet until we get to like hypothesis test stuff. That's where one-tail, two-tail differentiation will come into play. Essentially, what you would just need to know for this exam is when I look at a t-table, alpha over 2 is the one-tail area, alpha is the two-tail area. So we're working with a 95% confidence level, which means that alpha is 0.05 and alpha is 0.05. So my two-tail area, which corresponds to alpha, is 0.05. So I could go to this column right here. This is my alpha. This would be my alpha over 2. So follow-up question is, do we assume one tail on the coming midterm? And I believe most of your tables, like for the Z table, for your T table, the one that you're given, like the table A3 in the textbook, it's the same format as what I'm showing here, where you have the option of looking at one tail or two tail area. So you just need to know which one you're looking at. For the Z scores, like a Z sub alpha over 2, yeah, that's typically like the one tail Z sub alpha over 2. Okay, and let me get rid of this stuff here. Oh, whoa. Okay, my thing just kind of glitched out on me and I wasn't going to be too happy. So let's see where we were in this problem. I think we were basically finished with it. We have, this is our confidence interval. So yeah, went through this whole ordeal. 6.1 plus or minus this nonsense gives us 5.57 to 6.63. So another format that you would see this in is like 5.57 less than mu less than 6.63. So whether you write it like this or you write it like this, it doesn't matter. And B, interpreting your confidence interval given the context of the problem. So the confidence interval of 5.57 to 6.63, essentially we say that we have 95% confidence that the true mean, and then true mean of what? We're working with the context of the problem. So we need to say the context. So we are 95% confidence that the true mean of peak severity, true mean of days of peak severity symptoms for people not taking echinacea because they're in the placebo group. I'm just going to abbreviate it ECH. So this is essentially a formula like recipe you could say for this interpretation. You say we are blank confident that the true mean or true proportion, and then explain the context. And then, so I'll finish it out. We are 95% confident that the true mean of days of peak severity symptoms for people not taking echinacea is between, and then our confidence interval values. So 5.57 to 6.63. So state your confidence level, state whether you're talking about a mean or proportion, explain the context, give the values. And it's like the same kind of format for the other problem, like the other practice exam problem. Now we're going to do this again. We're going to construct a 95% confidence interval of the mean number of days of peak severity symptoms for those who receive echinacea treatment. So again, this is of the form x bar plus or minus t sub alpha over 2, n minus 1, and then times s over square root n. So that's the general form of the confidence interval. It's still a 95% confidence interval, so alpha over 2 is equal to 0.025. That means that t sub 0.025, comma, n minus 1. In this problem, n is equal to 101. We have that we're working with the echinacea group. So 101. So n minus 1 is 100. And then that's going to be equal to, let's go to the t table. If we choose to use alpha over 2, then I'm going to look at the one tail area. So going back, it's going to be the same column. 0.025 is my alpha over 2, otherwise known as alpha being 0.05. Now I'm going to go down to 100. So it's just the one below it, 1.984. So it's equal to 1.984. Now let's just go back and see what x bar and s are. So for the echinacea treatment group, the mean was 6.0 and standard deviation was 2.3. So we have 6.0 plus or minus 1.984 times 2.3 over the square root of 101, which is equal to, so 1.984 times 2.3 divided by the square root of 101. So this is approximately 6.0 plus or minus 0. Rounding a bit, 46, because last time I rounded 2 decimal places, I'm going to do it this time. Then this is equal to 6 minus 0.46 is 5.54, and plus would be 6.46. And now what we say, somebody asked how do we get the value of 1.984 again. And so the 1.984 on this t table here, it was because alpha was 0.02, alpha over 2 is 0.025, and n minus 1 is 100, and n minus 1 is the degrees of freedom. So I look here for 0.025 in the one tail area, and then the row is the n minus 1, which my row was 100, so that's 1.984. And somebody asked, how many decimal places should we round to on for the confidence interval? It doesn't really matter. 2 to 3, or 2 to 4, I guess. You're not definitely at least 2, I would say, at least 2 decimal places. But if you have more to be safe, that's probably better. And somebody asked, how do you know when to use the T sub alpha over 2 or the Z sub alpha over 2 formula? And that is whether it's a sample standard deviation that you're working with or a population standard deviation. So if you're using S, that means T. If you're using the population standard deviation, you use Z. And if you're doing a proportion, you use Z. So I'll also say that. Estimating proportion, you use Z. So I'll write out the 3 types of confidence intervals. So we have X bar plus or minus Z sub alpha over 2 times sigma over square root n. So if you have sigma, if you have the population standard deviation, you use Z. We also have X bar plus or minus T sub alpha over 2, comma n minus 1 times S over the square root of n. So if you're using the sample standard deviation, you use T. And then the other type is if we have a proportion, so P hat plus or minus, and this is where we use Z as well, times, and then this is P hat Q hat over N. And this last bit, why we use Z instead of T, it relates to this whole binomial approximation. A proportion is related to a binomial distribution, and binomial distributions are well approximated by normal distributions. So that's why we use Z. Okay. I'm going to erase these and we'll do the last part. So we compare these 2 confidence intervals. What do they suggest about the effectiveness of, oh no. I just accidentally exited out. That's not good. Give me one moment. Oh yeah, that PDF expert that I was using unexpectedly quit. So let me just open it back up. Hopefully it saved it. Oh, nice. It saved it. Okay, we're good. Cool. That's kind of nice that it saved it. So now compare these 2 confidence intervals. What do they suggest about the effectiveness of echinacea? So our first confidence interval, so for placebo, we had that it was 5.57 to 6.63. So that's what we estimate our true proportion of peak severity days for people who don't take echinacea, what they experience. And for treatment group, we have that is 5.54 to 6.46. These intervals are not very different. They're not very different. So this may suggest that echinacea is not an effective yeah, an effective treatment for the respiratory infection. Okay, so that was the last of that problem. And now just have 3 multiple choice problems. So opposite of one that you got on the practice exam, which was deductive reasoning. Inductive reasoning is A, arguing from a set of observations to a reasonable hypothesis, going from a hypothesis to a logical conclusion. The idea that the simplest explanation is likely the correct one or none of the above. And the answer is A. So arguing from a set of observations to a reasonable hypothesis. This was deductive. That answer. Now, question 5, holding everything else constant, as we decrease the significance level, the width of a confidence interval should, so let's just write out a confidence interval, like a general form of a confidence interval. X bar plus or minus, let's do z sub alpha over 2 times sigma over square root n. So it doesn't really matter what this will, the answer is going to be the same for any confidence interval. So let's think about what this is. We have some interval, right? So we have X bar, and then we go plus E and minus E. So, it's some symmetric interval. This distance is E, which is z sub alpha over 2, sigma over square root n. As alpha decreases, then z sub alpha over 2 actually increases. So for like a 90% confidence interval, the z sub alpha over 2, so like if alpha is equal to 0.1, z sub alpha over 2 is equal to 1.645. When alpha was equal to 0.05, so decreasing for a 95% confidence interval, z sub alpha over 2 is equal to 1.96. And I don't remember what it is if it goes further, but it continues this trend. So significance goes down, z goes up, which means that the interval would get wider because z is getting bigger. So this quantity here is getting bigger. So the width of the confidence interval should increase. And the last one, when the data from a simple random sample are used to estimate a sample mean, the maximum likely distance between the estimate and the true population mean is given by, so again, maximum likely distance, and let's see. I got a question, I think related to the last one, is significance level equal to alpha? And that answer is yes. So significance level is what alpha is defined to be. Like if you were to say what alpha is in English words, it's the significance level. So yeah, question 6, when the data from this yada yada, so maximum likely distance between the estimate and the true population mean is the margin of error. So that's just like this figure up here. It's this maximum likely distance, which is denoted E. So that's the multiplication of these two together, for the confidence interval X bar plus or minus T sub alpha over 2, comma n minus 1 times S over square root n. So the multiplication of these two is E, which is that whole distance here of the interval. So answer here is A. And yeah, that is it. So I think I'll stop the recording now and